Hello there. Last time we developed the equations of motion and then started off on free vibration. So, let me continue with free vibration. Free vibration for multi-degree of freedom structures. Okay. So, this is the topic that we will be dealing with in this lecture. Just to review what we had done last time, we started with the fact that the free vibration problem essentially became a solution to this problem. This was the solution, okay? And we saw that since both of these are symmetric and positive definite, therefore, you get both the solutions to this are n positive eigen values. And so, these are given as omega 1 squared, which is they, as I said, of course, when I put this, it automatically means that these are the eigen values and the natural frequencies are ordered. Okay. So, so this is the lowest frequency, okay, and the lowest frequency. So, therefore, what we have then is the following, is that you have omega 1, then you have omega 2, omega 3 on to omega n, okay, ordered in this manner, and corresponding to omega 1 you have phi 1, phi 2, phi 3 and phi n. These are the frequencies natural frequencies and mode shapes. Now, it is obvious we have not stated it, and that is that these are automatically undamped frequencies, okay? Mode shapes, these are the mode shapes, okay? Natural frequency omega I and mode shape and corresponding mode shape, Now, these are undamped frequencies, okay? And the issue then becomes is why are we spending so much time in getting undamped frequency, and that is because we accept here that since we are looking only at multi-degree of freedom frame problems, okay, therefore, the basic fact is that for these damping is significantly less than 1, and therefore, omega I and omega d I are practically the same. So, therefore, we do not really need to find out omega d I, we are happy with finding out omega I and going with it. Primarily because you can't really find out damped frequencies until and unless you have a C matrix also established. Okay? So, damping matrix. Now, note that the mass matrix and the stiffness matrix are properties that can be established for a given structure. Given the properties of the structure, given the dimensions of the structure, we can get the mass matrix and K matrix. The damping, if you remember, if you think back to your single degree of freedom, damping, you see how did we define? We said that, well, it was equivalent to a viscous dashpot. So, that is what we called viscous damping, and we said, well, that is proportional to the velocity, and so we identified a dashpot constant C, okay, and said, okay, it is C V dot, okay, and that is how we introduced the concept of energy dissipation. Now, the problem becomes that, in that case we saw that xi was equal to C upon 2 m omega, and we said that, look, we instead of looking at C, identifying C for a structure, we are going to identify xi, and we saw that, and another point is that during this course you will also have some laboratory experiments where you will see that xi is essentially a material related constant. Okay. So, therefore, there for a single degree of freedom it was very easy to define one xi, and then xi C was equal to 2 xi m omega, and from that we got C, and we could write it down, or we could actually write it down in terms of this thing. For a multi-degree of freedom structure, the problem becomes not a single C, right? It is actually a C matrix, right? If you write it in that form, you will have to develop a C matrix. And now, that is not such an obvious thing, as we will see later on in this class itself. So, the question then remains is that as far as multi-degree of freedom systems are concerned, we actually stop at, in general we stop at developing the undamped frequencies and accept the fact that the undamped frequency and the damped system frequencies are very close to each other. So, in other words, we are not really treating this that there is no damping in the system, we are just developing the undamped frequency problem, and we are getting that. Okay? So, therefore, the natural undamped frequency, but natural frequency, we are just calling it a natural frequency in this particular case. Okay? And there are certain important aspects here that you are likely to see, and that is that these mode shapes satisfy certain properties, and the property is the following. It is called the orthogonality property, and the orthogonality property says these are this is called as mass orthogonality, and this is called stiffness orthogonality. Okay. What this says is that phi I m phi j is equal to 0 for all I not equal to j, and phi I into k phi j is equal to 0 for all I not equal to j. Note that this is this is not this way, this is phi I transpose. So, this is a 1 by n, this is a n by n, this is a n by 1. When you multiply it, you get a scalar 1 by 1. Okay. So, this is the orthogonality property. Okay. Now, how do we prove this orthogonality property? Let us look at it. Let us consider that k minus omega I squared m phi I is equal to 0, right. So, if you look at this, we are seeing that k phi I is equal to omega m phi I. You accept that? Okay. Now, I've just kind of written it, you can write this. I've just taken this on the other side. So, it's k phi I minus omega I m phi I is equal to 0. So, therefore, k phi I is equal to m omega phi I. Accept that? Okay. So, now let us look at this. I am going to pre-multiply both sides. See, I can do that as long as I, if these are equal, if I pre-multiply them by some right, I can do that. I am sorry, this is I, phi I. Okay. I can do this. What I have done is I have just pre-multiplied by phi j transpose. Both sides of the equation I have pre-multiplied by phi j. Okay. So, this becomes what? This becomes the following, that phi j transpose k phi I is equal to omega I squared phi j transpose m phi I. What is this thing? This is 1 upon n into n into 1. So, both of these are scalars, both sides are scalars. Do you agree to that? Okay. So, now, this is one part, right. Let us look at this situation, that k minus omega j squared, right, into m into phi j is equal to 0, right. So, again rewriting this, we get it as k phi j is equal to omega j squared m j. Okay. So, now I am going to pre-multiply both sides, pre-multiply both sides by phi I transpose. So, if I do that, this becomes phi I transpose k phi j is equal to omega j squared phi I transpose m j. Do you agree to that? Okay. Now, these two are, what are these? These are scalar, right. So, now what I am going to do is, this part I will take its transpose. If I take its transpose, since these are scalars, the transpose will be themselves, right. So, therefore, if you look at it this way, okay, I can do, because this is scalar, a scalar's transpose is the same, is itself. A scalar's transpose is what? 1. Transpose of 1 is what? 1, right? It is a scalar. So, therefore, if I do that, if I take the transpose of this, then this becomes phi j transpose K transpose phi I transpose transposes itself is equal to omega j phi j transpose m transpose phi I transpose transposes itself. Okay? So, that is what we get, because a scalar transposes itself. Okay? So, therefore, this is what I get. So, now from the two things, if I look at what I have, okay, what do you get? Well, one we got in the previous one, we got that, look, phi j transpose K phi I is equal to omega I phi j transpose m phi j. So, let us write that down. So, if I write that down, this is turning out to be equal to phi j transpose K phi I is equal to omega I into phi j transpose m phi I. And if I look at it from this one, I get it as phi j transpose K transpose phi I is equal to omega j squared phi j transpose m phi I m transpose. Okay? So, this is what we get from the two sides. Now, what is K transpose? The transpose of a symmetric matrix is itself. So, K transpose is equal to, because they are symmetric. So, what does this equation become? This equation becomes phi j transpose K phi I is equal to omega j into phi j transpose m phi I. Do you agree to that? Now, but you see this is a scalar, right? So, if you look at it as a scalar, then if you look at it, what happens then? That this divided, okay, this, if you look at this one and this equation are identical, but omega I squared is not equal to omega j squared. Do you agree to that? Because they are two different natural frequencies, so they are two different frequencies. So, if you have a situation like this, where omega I and omega j are not equal to each other, but both sides are identical, what does that mean? By definition, that means that phi j transpose K phi I is equal to 0. Okay? So, that is the first proof. Now, in similar way, because you see, once we put it in that way, we can always say that, look, if this is equal to 0 and omega I squared and omega j squared are not equal to 0, then automatically it is also a mass orthogonal. Okay? Now, this is actually a very, very important property. The property of orthogonality is a very important property, and this we will see is actually going to help us the orthogonal the fact that phi I transpose m phi j is equal to 0 and phi I transpose k phi j is equal to 0. These property for all I not equal to j, for all I not equal to j. Okay? So, this orthogonality property is fundamental to response analysis. Okay. We'll see later that how to get how to use this orthogonality. Okay. Now, the question becomes that you see one of the major issues that happens is that since mode shapes are just a shape, so you can only this matrix K minus omega squared m equal to 0. Since this is determinant is 0, so therefore, as I said, its rank is n minus 1, and what you do is this you cannot evaluate explicitly. What you get is that you will get a shape which is in terms of some, like for example, I can put it this way. I can find out n in terms of 1. Okay. So, that is why this is a shape rather than a specific value, because this is rank n minus 1. So, you only have n minus 1 rank n minus 1. What does it mean? It just means that it is essentially n minus 1. You see, you have n equations here, right? There are n equations to solve for phi I, okay? Because this is a matrix. This becomes a matrix, something, an X matrix. So, X into phi I is equal to 0 essentially represents n simultaneous equations. Okay? Now, ideally, if X is determinant is not 0, then X is of rank n, and you can explicitly get, it is like this, right? Ax equals to y, this is a simultaneous equation. As long as A is of rank n, you can, and y is given, you can always find out x by solving simultaneous n simultaneous equations. Okay. The problem here is that this determinant is indeed 0 and it is of rank n minus 1. So, essentially what it means is that you only have n minus 1 independent equations. So, when you have n minus 1 independent equations, you can only get n minus 1 values. Okay. So, that means that, what does that mean? That means essentially you are getting, you do not know one and you are getting all of them in terms of the other. Okay. Now, this brings in a certain amount of randomness in the mode shape. Okay. And why is that? Because essentially, well, you may choose phi n to be 1, I will choose phi 1 to be 1, it will be the same shape, but it will look completely a different mode shape. Okay. So, the thing is that now a lot of people say, well, what do we do? Well, you look at the mode shape and you choose the highest value as 1, so that every other value is less than 1. Now, my question is, these are all fairly random processes. So, therefore, there are a specific type of mode shape which everybody would get the same mode shape, and that mode shape is called as an orthonormal mode shape. What is an orthonormal mode shape? Typically, see, phi I transpose m phi j is 0, but phi I transpose m phi I is not 0. Okay. This is some, I will call it as m I, because this is, after all, since these are dimensionless and this is a mass, this scalar quantity, note that this is 1 by n, n by n, n by 1. So, this is a 1 by 1, this is a scalar. Okay. So, if I do this, okay, then an orthonormal mode shape is one where I'll call that orthonormal mode shape by a hat, phi I transpose m phi I hat is equal to 1. This is the definition, then phi I hat is an orthonormal mode shape. Okay. So, now given, so I find out any one, how do I make it orthonormal? Well, very easy. If you look at it, this becomes very, very simple. Phi I hat is equal to 1 upon root m I into phi I, this phi I. Okay. So, use any phi I. So, I mean, no, it does not matter how you get your phi I. Once you get phi I, you do phi I transpose m phi I, you get your this value, and then the orthonormal is 1 upon root m I into phi I. This everybody will get the same shape, and if you know, it's obvious, because if this is the case, just plug it in, you will see 1 upon root m I phi I, okay, transpose, and 1 upon root m I phi I transpose. So, this phi I transpose becomes m I, 1 upon root m I into 1 upon root m I becomes 1 upon m I, 1 upon m I becomes 1. So, automatically this is your orthonormal mode shape. How to evaluate an orthonormal mode shape? And this orthonormal mode shape is unique. Okay? This is unique. So, now the question becomes is that we have looked at mass orthogonality, we have looked at stiffness orthogonality, phi I transpose k phi j is equal to 0 for all I not equal to j. Now, the question becomes, are there, I will just so that you can see it, for all I not equal to j, for I not equal to j. Are there any other ortho? In other words, are the mode shapes orthogonal with respect to any other matrix? That is the question that comes up. Are the mode shapes, we have seen mass orthogonality, we have seen stiffness orthogonality, and the question then becomes is that are there any other orthogonalities in the system? Okay? And this was something that Cauchy Tom Cauchy, who was a professor of structural engineering at Caltech, he discovered that indeed there are other orthogonality properties that you can get. Okay? And he proved that there are a class of orthogonality which are given by phi I transpose into M into M inverse K into B into phi j transpose is equal to 0 for minus infinity to infinity. In other words, orthogonality conditions exist for an infinite number of values. Well, let us look at a specific value. Okay? Let us see, I will show you what this one is, how this one is proved by looking at a particular value. See, put b equal to 0. What does b equal to 0 mean? That means this one to the power of 0. So, that means that is just my mass. So, if you look at this, b equal to 0, I have phi I transpose M into M inverse K to the power of 0 phi j, which is nothing but phi I transpose M phi j, which we know is 0. B equal to 1, phi I transpose M into M inverse K into phi j. What is M into M inverse? I into K, K. So, this is equal to phi I transpose K phi j, which we know is equal to 0. Let us look at b equal to 2. B equal to 2 is phi I transpose M inverse K into M inverse K into phi j. Okay. Let us see what this is. So, if you look at this, M into M inverse is nothing but I into K is this. So, this is equal to phi I transpose K M inverse K into phi j. So, let us look at this. What is that? That is equal to what? Well, let us see. Let us look at this particular one, and that is let us look at the term K inverse, K into M inverse. Okay. Now, if you notice the following, that what is K phi j? Note that K phi j is equal to omega j squared M into M phi j. Do you agree to that? We have already seen it. So, if I substitute this by omega j squared into M phi j, then what does it become? If you look at M in omega j is a scalar, so I can take it outside. So, I get M inverse into M, which is I. Okay. I into K is K into I is K. So, again I get phi I transpose K phi j, okay, into omega j squared, which is non-zero. Okay. So, obviously, this is equal to 0. Okay. And in this manner, we can keep showing that indeed you can, I mean, so I can show b equal to -1. I don't want to get into that, okay, because -1 all it means is the inverse. Okay, what is b -1? Let me just show it, because you have to understand what this essentially means. Okay, this essentially means is that b is equal to -1, all it means is phi I transpose M inverse K to inverse. Okay? And what is the inverse of K inverse? It becomes phi I transpose M K inverse M inverse inverse, which is this. Okay? Now, I can say that look, M j, okay, M into j is equal to 1 upon omega j squared into k j. I have just put this omega j squared, which was here, on this side. Okay. So, I can then put this in here, plug this in here, and so this will become 1 upon omega j squared phi I transpose M k inverse into k phi j. Note that k inverse is basically I. So, this becomes M into I 0. So, you see, I have shown to you, okay, this was, I mean, Cauchy actually developed it in a much broader sense, but I have showed it to you that it is indeed possible to show that all values of B from -infinity to infinity actually have an orthogonality condition built into it. Okay. Now, this makes it very, very interesting, and that is that we can now start talking about damping. Now, you may ask that why am I talking about damping in this particular state? Because you have to understand that we have to develop the concept of damping. Okay? So, because ultimately it goes down to the fact that if you have damping, you need to know the damping. Otherwise, if you do not incorporate damping into your system, okay, there are issues. Now let us look at this. How? So, now the question becomes, how do I get a C matrix? Now, you see, there are various reasons behind it, and that is that why get a C matrix? Well, you need a C matrix so that you can make it look like this. Where these are the inertia forces corresponding to the degree of freedom, these are the damping forces, these are the elastic forces, and so this plus this is equal to the applied load. Okay? So, I mean, it is just a question. Now, later on I will show you that you really do not need to find out C, but the question comes out is that, well, I mean, suppose I need to find out C, how do I go about it? Note that in the earlier case, in the single degree of freedom case, C was actually evaluated from 2 xi m omega, and I knew this from experiments. I know this from experiments. So, once I do that, I know this, and therefore, this was evaluated for a single degree of freedom system. Okay? So, essentially it comes back to having to come from that you get this from experiments, and from this you get. So, understand that this is a derived quantity. It is a derived quantity. So, therefore, even in a single degree of freedom, this was derived, and so in here C is again a derived What is it derived from? Xi. Okay. It basically comes from xi. Now, the question here is the following, that there was only one natural frequency and therefore, only one xi. In this particular case, what do we have? We have omega 1, omega 2, omega 3, omega n. So, I have n frequencies, okay? And the question then becomes, is that, well, corresponding to these, I have phi 1. So, I have mode shapes, and these mode shapes satisfy the orthogonality condition. Okay? But in addition, the question now remains is that, well, this is a mode. Is there a xi 1? Can I find out from experiments? Can I find these out? Okay. Can I find these out from experiment? Unfortunately, this is difficult, but today we can get it. We can experimentally determine these. Okay? Of course, you know, if we say that the frame was made from one material, we have stated that, look, if it is made from one material, we said that for the material, your xi was a function of the material. So, if we are using one material, then we should say that these are all equal to each other and equal to xi, which is the material's xi value. And in fact, why not? You know, although, you know, we can get for every frequency, I will not get into that right now how we do it, but we can. And the question then comes down to the following, and that is that essentially, if we say that the frame is made up from one material, then a material has a damping. That was one of the first things that we said. Otherwise, it was going to get very, very difficult, because for every material, I mean, you know, for every structure, we would have to do an experiment to find out its xi, and you know, you have to build the structure to find out its xi. Now, to design the structure, you need the xi. So, it is a chicken and egg kind of a situation. We got out of the chicken and egg situation by saying what? Well, if it was made from concrete, we would know what xi would be. Remember, I said that experimentally it has been shown that if concrete is subjected to low strains, xi is about 3%, 0.03. If it is subjected to relatively high strains, xi is equal to 5%. If it is subjected to very high strains, xi is equal to 7%. For steel, well, it is about 1% for low strain, it is about 2% for medium strain, and up to about maybe 3%, 2.5 to 3% for so as long as my building is made from one material, okay, I have no problem. I know the xi and I can put that xi in every mode. So, therefore, you know, damping is being incorporated, only problem is it is being incorporated in every mode, and how does that help me? Well, ultimately, if you look at it, I need, you know, I can actually, remember I developed a numerical method, the Newmark-Better method, the linear acceleration method. Well, look at this, you know, this, you know, all that does is it sets up a kind of a del k tilde into delta v is equal to p, right. Now, you know, so that was, remember we did that, we said that delta k, I mean sorry not k, delta k, k tilde into delta v is equal to delta p, and that is how we found out delta v. Remember we solved that? Now, here also if we do that same thing, all that we will get is that we will get a k tilde into delta v into delta p. All we will have is n simultaneous equations. So, the ODE can be transferred into simultaneous equations, which can be solved using any simultaneous equation solver. Okay. So, therefore, it goes back to the fact that to get this we need C matrix. So, how do we get the C matrix? Now, the question here is the following, that damping, as I showed you that in single degree of freedom, damping had a very eclectic beginning. In multi degree of freedom damping had a very interesting concept. There was this business when Rayleigh, we will show later why proportional damping was important. I will tell you what proportional damping is. I am just introducing the concepts here. Rayleigh said that, look, take C is equal to, okay. Now, you can take mass proportional damping. Mass proportional damping would be C is equal to alpha m. Stiffness proportional damping, C is equal to beta k. Okay. So, now, and Rayleigh said, well, this is a combination. It is a combination of mass proportional damping and stiffness proportional damping. Okay. So, now the question becomes, so what? We still do not know. Let us look at first these, then we will look at this, okay. And then we will slowly look at a broader kind of damping, which is called as Cauchy damping. I will come to this Cauchy damping later on in the next lecture. Okay. The question here then becomes is that how do I find alpha and beta? Because, or if it is mass proportional damping, how do I find out these proportionality constants? So, the question is alpha, beta, how do I find these out? Okay. And multi-degree of freedom problem, I am just identifying this, and I will come back to this much later. I will come back to this not in the next lecture, we will come back to it later to show that getting alpha and beta is easy, okay, provided you define the damping in each mode. Remember this, that this is necessary. This is necessary. Okay. This is a definition, and of course, typically we define them to be the same in all modes, but this is definition is essential to getting C matrix. Okay. And this in essence we will see is overall how damping will be taken into account, but I am going to get out of damping now and come back to the concept that essentially damping is important because dynamic characteristics in each mode. Damping is an integral part of the dynamic characteristics. These are dynamic, and as we have seen, that the response of a structure is determined by its damping characteristics. So, it is very, very important for us to define dynamic characteristics very appropriately, and that is why I brought in the concept of damping. I want to end with one final comment, and that is, there is a reason why we do this, that we put it the highest frequency and the lowest frequency as the first mode. Why? Well, this mode, the lowest mode, is also known as the fundamental mode. Fundamental mode of vibration of the structure. Okay? I will talk about this more in the next lecture. Thank you. Bye.